So my name is Levester, and this is my post-lab tutorial quiz. I decided to do problem 5P63, and after reading the prompt, the first question asked me to predict the speed of a star going around the center of a galaxy in a circular orbit as a function of the star's distance r from the center of the galaxy, assuming that almost all of the galaxy's mass m is concentrated at the center. Okay, so first, I know there's two equations I want to use. I want to use the gravitational force that will be acting on the star, which is going to equal the g constant times the mass of the star times the mass of the galaxy times r squared. And I also want to use the centripetal force, since that's the force needed to keep the star in its orbit, which is Fc is equal to the mass of the star times velocity squared divided by r. Now, this is based on Newtonian physics, and in Newtonian physics, the mass m is treated as the center of the mass, which in this case would be the center of the galaxy, which is where all of the visible matter is concentrated. And in order to find v squared, I need to set these two equal to each other, because the centripetal force that keeps the star in orbit has to equal the gravitational force of all the other matter that's also in the galaxy. So by setting this equal to each other, g m1 times m over r squared equals m1 v squared divided by r. After some calculations, I find out that v is equal to the square root of the g constant times the mass of the galaxy divided by r. Now, this equation right here contradicts Rubin's fineness, in that the equation shows that the star's velocity is inversely proportional to its distance from the center of the galaxy. However, Rubin stated that no matter how far away that the star got from the center of the galaxy, its velocity would not increase, or would not decrease. So with that being said, you could say that this equation could also follow that situation if you kept m directly proportional to r's increase, and in that way v would stay constant. So but as you get farther away, with the increase in mass, you notice that there isn't as much visible mass farther away. So in order for this to stay true, that means there must be some type of invisible mass farther away in the galaxy that keeps this equation consistent. And we cannot see this matter that's farther away in the galaxy, because this matter does not absorb light or other forms of electromagnetic energy like the mass that's near the center of the galaxy. And that is my post-lab tutorial quiz, and thank you.